Welcome to section 1.3, day 1, limits. Today's objectives are to know what a limit is and to estimate limits graphically and to use one-sided and two-sided limits. First, let's talk about what a limit is. So the concept of a limit is that if you change the value of f of x as it approaches a unique value. So if you're looking at your x-axis down here, we're going to be coming into this c value on my x-axis. And as we come in from the two sides, what is happening to my y values? Well, my y values are going down as I come in from the left, and they're going up as I come in from the right. And they're approaching a y value. So as long as both sides from the left and the right are approaching the same y value as we get close to that c value on the x-axis, we have a limit. And so what this is we have this notation here on the bottom, right there, where it says the limit as x approaches c of f of x is L. And L is your y value that you are approaching. So like it says, you read this as the limit of f of x as x approaches c is whatever that value is. This is the idea of a limit. And limits are very important later on in math. We use them extensively when you get into calculus. Today we're going to introduce you to what a limit is and how to find them, both graphically and using tables of values. This is the idea of a limit. We're going to get closer and closer to some x value, and as we get close to that x value, what's happening to my y values? If from the left and right we approach the same y, we have a limit. If they approach different values, we don't have a limit. Another thing with limits is that the limit is independent from whatever the function value would be at that point. If you look at the graph on the left, you will notice there's a hole. Where the x is c, there's a hole there. That means that c, the function f of x at c, is not defined there. You don't get a y value back. But we are approaching that L value where that hole is from both the left and right sides. So we still have a limit there. Whatever that L value is, where that open hole is our limit because both the left and right sides are going to it. When you look at the one in the middle, has the same graph, except for now we've added at the top of the graph, there's this closed circle. So the curve has a hole in it still, and the left and right sides are approaching that hole as we get closer to C from left and right sides. But the function g in this case is defined at n. Well, we don't care what's happening at the value of c. We just care what's happening as we get close to c from left and right sides. So g of c in this case, if we put c into the g function, we would get back the value of n. But we still have the limit of L, because as we come in on this curve from the left and from the right, we are approaching this open circle. So the limit is independent of the value of the function at a specific x value, or in this case, a c. And then you'll see the one on the right, where they're using an h function. Now it's the same curve, but now we have a closed circle on the curve. In this case, the limit is the same as the value of the function. This one's a little bit easier to understand that, where we're approaching this L value, and the function is also worth that L value. This is the idea of a limit, though. We do not care what's happening at whatever x value we're looking at. We just care what's happening as we get close to it. So you're going to see that as we go through the slides today. So here's a limit example. Here is something you will need to be able to do when you are doing your assignment today and later on, of course. It says, find each limit graphically. So in your homework, you'll graph and see if you can figure out the limit from the graph. Then it says, support your conjecture using a table of values. So first we have our function, f of x equals x squared minus 16 over x minus 4. When you graph it, this is a graph you get. Now on your graphing calculator, you won't necessarily see that little hole there where x equals 4. On your graphing calculator, it's going to look like it's a solid line. But we can look at what's happening as we approach 4. So here's my 4 on my x-axis, And as I get closer to it, what's happening to my y value? My y value, and my scale is by 2, by the way, on the y. We're going at 2, 4, 6, 8. We are approaching 8 from the left side. And then we're going to come in from the right side. We're also approaching 8 as we're coming into our x is 4 from the right. So our limit, graphically, when we look at it, is 8. So next, we are going to use a table of values to show what's happening with this function. So here we have the equation I showed you on the slide. And as you get close to 4, you'll notice that it looks like a solid line, like I said. So the graph, when you look at 4, this is all scaled by 1, by the way. If you go to 4, we are going up to 8, just like what I showed you on the slide. So now when we do this to show it using a table, to justify using a table, this is what we have to do. So my equation's put into my y1. So I'm going to go to my table set. So second table set. I am trying to see what's going on when I have x equals 4. So I'm going to type in 4. Then I have this delta table here. This is my step, which is going by every time. I'm going to start with 0.1. All right, so this is 1/10 away from 4. From here, I'm going to hit second table. And you'll see here when I do my table, there's an error where 4 is. That's what that hole is that I was showing you on the graph on the slide. So when you did your graph on the calculator, it doesn't look like there's a hole there, but there is. There's an error there because it's undefined at x equals 4. Well, I want to see what the numbers are 1/10 away from 4 on both sides. So here we go. At 3.9, I go to 7.9. I'm going to put that on my table. At 4.1, I get 8.1. That was in my table. So let's see here on my, right, here's my table. Here's that 3.9 goes to 7.9. Here's 4.1 going to 8.1. Then I'm going to go back to my table and do another table set. This is sort of tedious, I know. So instead of going by 0.1, I'm now going to go by 0.01. And I'll go back to my table again. Second table. So now if I scroll it, you'll see my 4s right here on the bottom. And at 3.99, I get 7.99. That'll be another piece I put on my table that I'm going to create. I'm going to scroll down so you can see what happens at 8.01, or 4.01, sorry. 4.01 goes to 8.01. This is in my table. 4.01, 8.01, 3.99, 7.99, and I'll do it one more time. I'm going to go to the thousands. So I go back to my table again, second table set, and I'm going to change my delta for the table to 0.001. Here we go. I want to get back to 4. Now we go to table. Again, you'll see my error, like I said earlier. Here's my 4.001 goes to 8.001. When I scroll up, my 3.999 is going to 7.999. And what you should notice is that as you come in from both the right, which is from here, 4.001, getting closer and closer to 4, and I'm coming in from 3.998, 3.999, I'm getting closer and closer to 4, I am getting close to what's halfway between these two numbers. They both are getting closer and closer to 8. This is justifying using a table. They are a little tedious to make. This is what you have to do for a few of your problems today. Use your table, and you will do different steps to create this table that I have right here. Like I said, here's my 8, and as I'm coming into my table from the left, I'm getting closer and closer. You got 7.9, 7.99, 7.999, and it's going to keep doing that. And I come in from the right, I get 8.1, 8.01, 8.001, so it's getting closer and closer to 8. So we look at it graphically, we justify it with a table. That's part of what you do today. Look at a graph, see what it looks like, and then use a table to support it. Quite often when you do your table, you will have an error where you're trying to evaluate at, but we're looking at what's happening as we come in from both sides. So now we have what we call one-sided limits. We've talked about them already, but this is how we put together the notation. Because sometimes we just want to see what's happening from one side. We don't care what's happening from both. We just want to see the behavior, what's happening from one side. So we have left-handed limits and right-handed limits. And the notation's similar, except for when we come from the left hand, we're going to have the limit as x approaches c, and you'll notice it has an exponent that's a negative sign. So x approaches c from the left of f of x is L. So we have that negative as an exponent. It's telling everybody we're coming in from the left side. Similarly, when we come in from the right side, we're going to have x approaches c positive because we're coming in from the positive side of the number line. So this is how we notate when we're doing a one-handed limit or a one-sided limit. Left hands have a negative, right hands have a positive. And then when we do these, you're going to find some, when we do the left and right hand limits, the both sides do not go toward the same number. So to have a limit, the left and right side must be the same. And that's what it says on the bottom here. The existence of a limit at a point. So the limit of a function f of x as x approaches c exists if and only if both one-sided limits exist and are equal. So the limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right f of x has to be the same number. And if both of those things happen, then we will say the limit as x approaches c with no negatives or pluses in it, just x approaches whatever c value is of f of x is that L number. So left and right hand sides have to be the same. If they are, then we have a limit. So here it says, estimate each one-sided or two-sided limit if it exists. So I have a piecewise function here, and it's graphed on the right. We have the f of x equals, and then we have negative x squared minus 1 when x is less than 1. We have x plus 2 when x is greater than or equal to 1. We're going to look at the limit as x approaches 1 from the left. So we're going to be approaching 1 from the left, and you'll see the arrows there on the graph. We're coming in from the left side, and as we do that, we are following the bottom curve. So we're coming in, we're following this curve around right here, and we get down to negative 2. Then it says, look at the limit as x approaches 1 from the right, the positive side. Now we're looking at the upper line here. And so we're going to come in, we're coming down here, and we're getting closer and closer to 3. Then it asks, the limit as x approaches 1 of f of x equals. When you look at this, the left and right hand limits go to different numbers. So that means there is no limit, and we have a does not exist. That's what D&E stands for, does not exist. There is no limit at x approaches 1 because the graph goes to two different y values at 1. So this one does not exist, and that's what you write. D&E works, or you could say does not exist. All right, let's look at another one. Here we have again, estimate each one-sided or two-sided limit if it exists. Here we have the g of x equals x squared minus 1 when x is less than 1. And we have 1/4 x minus 1 when x is greater than or equal to 1. This time we're doing the limit as x approaches 0 from the left of g of x. So again, we're coming in from the left, so we're following this blue line right here, coming down until we get to x is 0. We are approaching the y value of negative 1. Then we're going to come in from the right side where it says limit as x approaches 0 from the right, the positive side. We're going to follow this line down. And it's also approaching negative 1. The last thing it says is the limit as x approaches 0 of g of x equals. The left side and the right side are both approaching negative 1, so my limit is negative 1. That's my L. The last one we have is find the limit if it exists. So we have the limit as x approaches 0 of h of x. We're trying to see as we get close to 0 of this function, h of x equals x squared minus 2 over x. The graph there is on the right. So we're going to approach 0 from the left. It says the limit as x approaches 0 from the left of h of x. So we're coming in, and we're going to go up our curve right here. And as we get closer and closer to 0, from the left side, the negative side, we are going to positive infinity. Then it says, do the limit as x approaches 0 from the right. And here, we are coming in from here, we get to the line, we're going to follow it down. And this is going to negative infinity. And then it asks, the limit as x approaches 0 of h of x equals, in this case, the left side's going to positive infinity, the right side's going to negative infinity. This is a does not exist because they're going two different directions. If they were both going down or both going up, we could say there's a behavior there. We would say it's a limit and what that is, but they're both going different directions, so there is no limit there. If you didn't recall, there is a vertical asymptote at 0. That's why it's doing what it's doing on the graph. All right, that is all for day 1, looking at limits. We looked at what limits are. We estimated limits graphically. We used tables to justify what we're saying, and we used one-sided and two-sided limits. Thank you for watching, and have a nice day.